Another flow measuring device is the Pitot tube or pitostatic tube. It is known as both of these names. This is a very intelligent piece of device and very simple. I would say probably the simplest of all we have used before to measure flow. So the Pitot tube is used basically first is measure the velocity. It measures velocity and then we can convert it to flow. Because we know the equation flow rate is velocity times the cross-sectional area of the pipe where the flow is happening. So if we know the velocity of the fluid and then this cross-sectional area, then we can calculate the flow rate. So let me show you how a Pitot tube works and how it looks like. So imagine that this is the flow, the pipe where we have flow going on. So if I try to draw the velocity profile, it's going to look something like this. Let me just draw it and then I'll explain. So when the fluid is flowing through this pipe, as you can tell, the particle that touches this wall has a zero velocity. So the velocity at the wall is zero. And the highest velocity would be at the middle. So this is where the velocity is max. So the velocity profile will look something like this. So it's going to be zero at the wall and it will increase at the middle. So in the fluid, now think about this. So we understand that velocity at the wall is zero, velocity at the wall at zero, and the max in the middle. Now look at this. If I place a manometer here, a small, it's filled with water, the air is flowing through that. So this is a manometer. And I have a hole here. So when the fluid is flowing this way, it has pressure everywhere. So according to Pascal law, the pressure inside this pipe, if we ignore the small losses, they will be same. So when it pressurizes the manometer fluid, because you have high pressure here, let's say the atmosphere has less pressure. So it will create a pressure difference, assume that is the pressure difference. Now, because there is no velocity head at the wall, because the velocity is zero, this pressure difference is called static pressure. So PS. So this pressure difference is the static pressure difference or height of phase. Now, if I have another manometer, let's say set up a manometer like this, connect in the middle like that. So I have a manometer here, flow is coming this way. Now at this point, I have both. I have this fluid pressure inside the tube. Also, I have velocity. So I'll have more displacement of the manometer fluid. Let's say this is the amount of displacement by the manometer. So this is the pressure that has both dynamic pressure, the velocity head, and the static head. So we can say the total pressure difference or the total height difference, T, H, T. So total pressure at this point is basically because of the velocity head or velocity pressure, the dynamic pressure plus the static pressure. So now let's say convert this. We can measure this HT and then also the static head. So we can say here P equal gamma H. Gamma is this is for manometer fluid because it's the manometer fluid height change and then the total height change by this. And then the dynamic head we can write half rho V square plus this static pressure gamma of manometer fluid times the static change of height. If I solve for velocity, I'll get square root of 2 gamma of manometer fluid times the height of total height minus the static height divided by the fluid density. Now this fluid density is the fluid inside the pipe. So this rho is inside the pipe. So that's the fluid density. And then the gamma of fluid, that's for the manometer fluid. So if you just convert it, we know that gamma equals rho z. So we can actually write it for rho as well. So that's going to be V is equal to, just replace that gamma of manometer fluid with rho z. So we'll have 2 rho of manometer fluid z and then ht minus hh divided by the rho of the fluid that is flowing inside the pipe. So the density or gamma, their fluid property, G is a constant. We can measure HT and HS, so we can calculate the velocity. Now once we know the velocity, then we can calculate the area, cross-section area of this pipe, and then flow is velocity times the area. Now let me show you one more way of measuring the pressure difference. Now, a lot of times electronics devices are used. So there is a thing called piezoelectric material. So which is a kind of like a pressure transducer. It is a pressure transducer, not kind of like. So imagine that I have a tube that is connected like this. So this is so flow is coming this way. So instead of a manometer fluid, let's assume that right here I set up a piezoelectric material, which basically works as you compress, as the pressure increases, the voltage, it generates some voltage. So we can electronically measure the pressure difference delta P, which is basically the dynamic pressure of the so related dynamic pressure, because the static pressure will be cancelled out. So you got a static pressure PS here, pressure is everywhere. So there PS, so everywhere. So this pressure difference, if you connect this like this, you can directly measure the pressure difference. Then velocity would be, and this is of course for the fluid, velocity would be square root of 2 delta P divided by rho of the fluid that is flowing inside the pipe. So you can measure using an electronic device the velocity. So pitot tube is, you could either measure the velocity, or after measuring the velocity, you could measure the flow as well once you calculate this cross-sectional area. There are, I would say, at least 50-60 pitot tubes set up in any aeroplane. So you will see a bunch of pitot tubes they're measuring velocity. So they have huge application in the lab, in the industry, aeroplanes, buses, everywhere. You want to measure the velocity or flow, that's probably the one of the easiest way to do it.